Okay, good afternoon, everybody. On behalf of the Department of Operations and the Weatherhead School of Management, I'd like to welcome you to our seminar today and introduce our speaker, Dr. John Holland from University of Michigan in Ann Arbor. Professor Holland is a jack of all trades. Well, maybe not all trades, but certainly a lot of trades. He did an undergraduate degree in physics at MIT and worked for a few years at IBM before deciding he did want to go back and get a PhD. Started his PhD work at the University of Michigan in mathematics, and ultimately became very interested in computing and computer science. And so he finished with a master's degree in mathematics and then went on to get a PhD in communication science, which later became computer science. As you probably are aware, this is one talk of our Darwin Year celebration. And there's a very specific reason why we were honored to have John here. And that's because some of the greatest work that he has done is in the development of genetic algorithms. These are algorithms which are designed to solve very difficult problems in which you have a large number of possible solutions, and you want to find the best one according to some measure, whether it's profit or cost or whatever. And John developed an algorithm for maybe not finding the best solution, but certainly finding a good solution based on analogies with the way genomes divide, and in particular, crossovers. So I'm sure he's going to talk a little bit about that today. And then he wrote quite a well-known book called Adaptation in Natural and Artificial Systems. I believe it was 1975, and it's still in print today. And that led him to an even broader field of complex adaptive systems, which is an area that's very close to my heart. I've been doing research in that area for the last 6 or 7 years myself. John is a founding member of the Santa Fe Institute, which is the premier research institute in the area of complex systems. He is also a MacArthur Fellow and has a number of other distinguished awards. So it's a great honor for us to have him here today. And he's going to give us a talk today about complex adaptive systems. So John, with that, it's all yours.
Thank you, Danny. Let's see, are we getting? Yeah. I looked very hard to see if I could find a Darwin mustache today, it being Halloween, but I wasn't successful. So unfortunately, you just got to see this face. So I'm going to talk today about complex adaptive systems, and briefly, a complex adaptive system is a system that consists of many individuals, which we'll call agents, just to have a neutral term. And I'll tell you more about this, but an agent could be anything from somebody playing the stock market to an antibody in the immune system. And so we are interested in agents that not only interact in large numbers, or at least many times in large numbers, but also learn as they interact. So in the case of the immune system, your antibodies actually get better and better at equaling out against the antigens. So, or in the stock market, people play, they don't do it the same way every day. And some of them at least improve their performance. So that's the kind of thing that I want to look at. No, wrong thing. Oh, this should do it. No. There we go. So here is a broad outline of what I'd like to do. I'm going to first talk about complex adaptive systems, and then I'm going to spend a little bit of time talking about the relation of theory and models to the study of systems. So often, theory is treated, especially these days, as speculation. And I want to try, if I can, to distinguish between just raw speculation and something that counts as a theory. Then I want to talk about this notion of building blocks. And the easy or quick way to say that is that in a certain sense, everything we understand in this world is in terms of building blocks. You never have the same exact sensory impression on your retina. As far as your retina and your eye is concerned, you have perpetual novelty. You never get the exactly, there are several million rods and cones in there, and you never get the same exact light pattern on there. So somewhere you've got to find what repeats in these various patterns you see. And so that means, in terms that I'll talk about, that you have to find the patterns I'm going to talk about are patterns that can be put together, and I'll call them building blocks. Genetic algorithms is an attempt to do crossbreeding to get new objects or agents from the agents you already have. And then finally, I'll spend a few moments telling you why it's difficult to do this cross-disciplinary research, especially as a young assistant professor. Okay. And I'm old enough now, it's okay to say that. So first, one thing we noticed early on when we looked at these various disciplines, and I just picked 4 here, control theory, economics, biological cells, and games, is that we could find similar things with different names in each of these systems. So control theory, you have the variables, so-called process variables. Economics, you have the activities. Biological cells, you have the things that generate the phenotypic characters. And in games, it's the board configuration. Well, you can go on and down the list, and I won't do all that. But at the bottom of this, you have something that's important in all these things, and that is whether it's called a control policy, or whether it's called a plan, or whether it's called a reaction network, or whether it's called a strategy. These all, from a formal viewpoint, have very much the same formal characteristic. And I'm going to try while I'm talking to convince you of that. Okay, so here's a little more careful description of a complex adaptive system. We have a bunch of things that we're going to call adaptive agents. We have a network of interactions, and generally these agents compete with each other in one sense or another. They each have, so to speak, their own objectives, and they're trying to attain these objectives, and amongst other agents that may have different objectives. We also have, in effect, a group of agents like this. We can talk about the aggregate. And if I'm talking stock market, the agents are the buyers and sellers, and the aggregate is something like the Dow Jones average, where I have some overall description of what's happening with the aggregate, often an average, but not always. And the thing that's important here is this works both directions. The aggregate affects what the individual agent does, and the individual agent, of course, affects the average. So this back and forth, this top down and bottom up, is a really critical aspect of systems like this. And the other thing is that in realistic systems, the rules, and I'll just call them rules for the minute, by which these agents interact are conditional. They say if something is happening out there, for instance, if the Dow Jones is falling, sell. So conditional interactions are very typical of the agents we're talking about, and this immediately means that these systems, from a mathematical point of view, are badly nonlinear. That is that anytime you have an if-then, you have a sharp change. And so you can't approximate it well with linear kinds of approaches. That means that almost all of statistics, almost all of differential equations, and so on, the very favorites of the physicists, just don't work very well for trying to build a theory of these complex adaptive systems. And this I've already said. Let me point out some of the problems and the reason we're so interested in these systems. If you look at a question of how do I encourage innovation? Or how do I control the internet in terms of things like viruses and so on? Or how do I predict changes in global trade? Or how do I understand the way markets work? Classical economics says that the market always clears. That is, the market most of the time is in equilibrium. Well, I think we only have to look at the last 3 or 4 weeks to see that that mostly doesn't apply. And why doesn't it apply? How do we provide for sustainable human growth? Again, lots of agents interacting in an adaptive way for their own ends. Preserving an ecosystem. There are a lot of gee whiz figures about ecosystems. In a tropical forest, a single tree can have as many as 10,000 species, not individuals, species of insects co-surviving on that single tree. That's just incredible. We don't really know about things like that in the northern temperate zone. You can walk 100 paces in a tropical forest and not see the same species of tree twice. Now, one real question there is, how does this system sustain such incredible diversity? What's going on that allows that system? Why isn't there some super animal or super tree? The immune system. This is something we'll come back to in a moment. But the immune system, clearly, with all the wide range of antibodies in that system, is an incredible system. In fact, it's the best scientific definition you have of yourself as an individual. Your immune system is so individual that you can't even take a skin graft from a sibling. So your immune system truly identifies you as an individual. Okay? Now, if you're going to do that, how do you control a system like that that's so incredibly specialized to you? And a part of the answer, and this is something we really want to know a lot more about complex adaptive systems, think about a vaccine. Inexpensive, and if it's vaccination for measles, it changes your system for life. This whole complex system, we call those lever points. And every complex adaptive system that we've studied closely has lever points. What we don't know is how to find them. We wind up with trial and error, and that's where you need theory. The whole purpose of theory is to tell you where to look. If we had a good theory of complex adaptive systems, we'd know where to look for lever points. And you can see that they're important. Each of these problems that I'm talking about has a lever point, or many of them. Okay, just so we get a little bit of a better idea about agents, if I talk about an organism, that's an agent in an ecosystem. If I talk about a firm, that's an agent in an economy. Antibody, immune system, trader in a market, department, business, and so on. Now, depending on what question you're asking, you may pick different sets of agents, even in the same system. I might pick a firm in an economy, but I might pick a whole country. Or I might pick just a particular industry. That depends on what question I want to answer. And this is the reason framing questions in the sciences is a good 90% of your task. Phrasing it well is the thing that lets you build theory. A word or two just about adaptation. I'm going to use that as a very broad term. And that's a term that if you do it rapidly, I'll call it learning. It may be cultural in that case. More slowly, that's typically what a biologist calls adaptation in biology. But I'm going to use it as a wide term that says that somehow this agent is changing its strategy or its plan, its rules, as it gains experience. And most people have either seen some discussion of the evolution of an economy or the evolution of an ecosystem. If you want to get good, solid examples, those are two areas where you can get a lot of both discussion and data. All right, what are some of the characteristics of these systems? And these are the characteristics that make them particularly difficult. One is, as we were just talking about in the tropical rainforest, there's no universal competitor. There's no optimum. And in fact, in most of these systems, it's very difficult to define even what you mean by an optimum. What's an optimum tropical rainforest? I don't think anybody would attempt, even a very good biologist, to do something like that. The diversity we've already emphasized. The other thing in these systems, because they are learning, is that innovation is a regular feature, and that's something we want to talk about, is this whole notion of innovation. But there are always new species arriving, and if you look at some rapidly evolving group like the orchids, it's just incredible how rapidly orchids are evolving. Darwin, by the way, wrote a whole book on orchids, so this was already of interest to him. It's a very nice book. The other thing, and I will talk less about that today, even though it's very important, is that these systems predict or anticipate. And even if the prediction or the anticipation does not come true, it still can cause the system to change course. And we've seen plenty of that recently in the market. You know, I think the market's going to fall tomorrow, and so I do some selling, and then I find out, in fact, it doesn't fall tomorrow. Well, it still changed the market. Not me alone, but some of those guys. All right. When it comes to innovation, the critical thing, and this is something that's really often overlooked, is what I'll call risk-taking. Now, you hear often in government and other places, people talk, and especially in football games, about a game plan. And at a certain level, that makes sense. But if you look at, say, a large corporation, a corporation isn't forced to move just in one direction. It can put probes out in several directions, and it can try this, and it can try this, and it can try this, each with a certain kind of risk. Now, one of my former students is John Seeley Brown, who is the chief scientist at Xerox PARC. And John said that if 95% of their research projects did not fail, in other words, 95% should fail, or they weren't pushing the envelope enough as a corporation. Now that's the kind of risk you're talking about, that, you know, only one project in 20 is going to succeed. Okay? Now, notice though that in these projects, your investment is pretty much limited. It's not, you're not, you know, putting the corporation on the line. You're putting some of your bottom line out, but you're not really risking the whole corporation. Now, just as an example, in a university setting, University of Wisconsin, they got a patent from one of their risky projects for warfarin, which is, if I say it in the crudest possible way, it causes rats to bleed to death internally. So it's a very good, roughly 20% of the buildings and the activities on the University of Wisconsin campus come from the income from that particular, whoops, do I just hit it again?
No. Oh, you just touch the screen, it's up there. You just
Oh, okay, we've got to go forward a bit. Oh, no. Okay. So the point here is that you do these risky things, they cost you a certain amount, but the home runs, the ones that really work, way more than pay back the initial risk cost. Now the trouble with complex adaptive systems in general, and certainly in, say, current economics, is that almost always corporations are judged on their current bottom line. How much profit did we make in the last quarter? Question is how to get credit for these risky projects that are costing money right now, but 10 years from now may be the price of survival for the corporation. And you only have to look to Michigan and in the automotive industry to get a great example of not looking ahead. The point is then, or the question, and this is a little bit like lever points, how do I find ways that I can do these risky things that don't pay off right away? And you all know if you play a game like chess or Weitji that it's these moves, the early moves that don't seem obvious, that enable you to become a good game player. It's not the obvious moves where I can check the king or something like that. It's the early moves. And that's the risk-taking. Okay, so the point I'm trying to make is really the second point too, that if I'm big enough, as an individual, I may not be able to follow many paths simultaneously, but as a corporation, I certainly can, if I have the will. And the last point is the one I've been talking about. How do I get credit assignment back to these poor researchers in their laboratories that made it possible 5 years later to get the intermittent windshield wiper on your car? These innovations make a difference. So let's talk about theory and models as prologue. And I love this cartoon from the New Yorker. It says, Please, Mrs. Sweeting, may I ask where we're going with all this? And, you know, it's not so obvious knowing what 2 plus 2 leads you, but if you think that happens, all you have to do is look around you and talk to anybody about theory, and you'll see that they have the same thing. Well, what's this going to do for us? I'm going to distinguish 3 kinds of models that are often confused in the literature, even by very good people. First, there's the more familiar model, which I'll call data-driven. And that's where we have a large amount of data, as in weather forecasting, or as in something like the Human Genome Project, or any of the, or in proteomics. We've got a lot of data, and we're trying to build a model that will take in that data and tell us something about what's going to happen, or how do we control it. Those models are really pretty familiar. Less familiar is the so-called existence-proof model. Back in the early 1950s, John von Neumann, whom some people would say was the greatest mathematician of the 20th century, John von Neumann built a model that showed that a machine could reproduce itself. So he demonstrated that a machine could reproduce itself. Before he put that model out, it was common in both philosophy and biology to say that only living organisms could reproduce themselves, because those were the only examples we had. Right as soon as he published that paper, within 2 years, all those arguments were gone from the literature, because here was a counterexample. It really showed that you could build such a thing. Okay, and then finally, and this is perhaps the least understood of these models, is what I'll call an exploratory model. And an example is where I have some mechanisms in mind, and it may be as simple as gear wheels and springs, but it could be as complicated as various structures for antibodies and antigens. I have some mechanisms or objects or agents in mind, and I want to see what will happen when I put them together. Now, that doesn't prove the real system will work that way. All it does is let me explore interactions. And in many areas, especially in complex adaptive systems, it's so hard to understand what these systems are going to do when you put these agents together that exploratory models become your major way, especially since very few parts of mathematics will help you. And then there's this point, and I used this morning, but I'll ask the same question to you. You didn't know you were coming to an exam. How many of you know who Eddington is? How many do not? Okay, not surprising. He was the man that first demonstrated that Einstein's theory of relativity really worked in the real world. And he did this in a very clever way. What he did was, and he's a very practical man, he was an astronomer. He waited for an eclipse of the sun in South Africa, and then he watched to see whether the position of the star appeared to move as the light rays from that star got closer to the sun. So Eddington was a very practical man. It's very interesting that he would say something like this: the contemplation in natural science of a wider domain than the actual leads to a far better understanding of the actual. And I couldn't have said the purpose of exploratory models any better in any way. It really says to me what exploratory models are all about. So I simply suggest that when you read a paper and you hear somebody talking about modeling or discussing modeling, the first thing to do is try to decide which of these 3 modeling techniques or ideas or tactics they're trying to use. Now, let me say some things we don't know. I said earlier, all these complex adaptive systems exhibit lever points. We know this by just looking. What we don't know is how to find them. And so we really do need some kind of theory there. It turns out that every complex adaptive system we know of has a kind of hierarchical organization. Again, think of a biological cell. You have the interior membranes, then you have the external membrane, and then you have the cells in organs, and so on and so on and so on. You think of a government, or you pick any one of those complex adaptive systems, you see it has this hierarchical organization. Why? Why is that so pervasive? What's the reason? There is no theory that tells us or even suggests the mechanisms that might yield these hierarchies. And something you'd think by now we should be able to do, especially since we've been fussing around with this for quite some time, is to find a model which really shows the kind of increasing diversity, the kind of open-ended evolution that we see in real biological systems. And again, there's not even a single good computer model that I know of that will exhibit this open-ended evolution. Really surprising after this amount of time. Now, I'm going to say some things that, with my colleagues say at the Santa Fe Institute, I can start good arguments with. One thing is, I don't think in the study of complex adaptive systems that we need a precise definition of complexity. And let me just give you an example. We have a perfectly good, actually several perfectly good sciences of biology. I don't know anybody right now who would attempt to define life in a precise way. So it's possible to study a subject without having a precise definition of the subject matter. And you can talk about several things like this and find that in very important topics that we study, we don't have a precise definition of the whole subject, but we have good definitions of parts of the subject. Now, I tend to, depends how cruel I'm being that day, I either call this the pile of sand argument or the bald man argument. If I have a pile of sand and I take one grain off at a time, when does it cease to become a pile of sand? Well, that's clearly an unanswerable question. I mean, there's clearly a time when it's a pile, and there's clearly a time when there are only a few grains down there. Somewhere in the between is when it ceases. The bald man version is take one hair out of my head at a time. When do I become bald? It's, anyhow, I'm one that I would personally, and several of my colleagues personally, would not spend much time trying to get a precise definition of things like complexity or emergence or several of these terms that are vague in one way, but it's possible to study them nevertheless. I think that things like poles, trends, averages, and so on, stability, complex adaptive systems really are not well studied this way. They don't settle down. If I talk about a living organism, the only time it's stable is when it's dead. And so there's these strong tools can give us some hints about what to do, but they're unlikely to solve these major problems for complex adaptive systems. There are some things that I think are of limited help, but as far as I'm concerned, and again, you're getting my opinion, too much effort has been spent in terms of the return. We hear all the time about chaos. The more precise definition of chaos, at least from physics, is that you have two initial conditions that are within epsilon of each other, and after some amount of time, they diverge so much that you might as well be doing things at random. The thing is, in most complex adaptive systems, take weather prediction, for instance, the data is being updated all the time. There's never enough time for this butterfly down in Argentina to cause the hurricane in the Caribbean. The data is being updated on a 6-hour basis at the very least. And so there are no time for chaotic effects to really have much influence. So my opinion in the study of complex adaptive systems is the formal theory of chaos is of limited use. Now, again, I could get in a lot of arguments. The other thing is network theory is a very hot topic right now, and it has certainly helped us understand some difficult things. And at the University of Michigan, we have one of the best network theorists going. His name is Mark Newman, and he's published some really key papers in this area. But as yet, they are not studying how networks change over time, except occasionally with random changes. And that, in a complex adaptive system where I'm trying to study interactions, is the key. How are these interactions between the agents, the network, changing over time? That's the whole name of the game there. Now, it's interesting, and some of us are beginning to push on this. If I look at networks in, say, these agents, between these agents, and I say these agents can only communicate by signals of some kind or other, which is reasonable, buy and sell orders, whatever it happens to be, then I can think of the network as changing because the signals are changing. And so if I go back underneath the network, there are ways that I can begin to understand the dynamics of the changing network and not just how signals flow over the network. So that's a possible approach. Okay, and here are some things that I think are promising. Agent-based models we've already talked about. One thing I should say there, and this is sometimes overlooked, take something like a flight simulator. Nobody builds a modern airplane without having a flight simulator that will simulate its flight. Who checks out whether the flight simulator is any good or not? It's not the programmer, it's a pilot. And an expert pilot flies that simulator just as if he were flying the plane, and he starts out very simply and he does some banks and so on. And if it doesn't act right, he goes back and says, this model's wrong, you got to fix it. Okay? What makes that possible? And this is the thing, if you're looking for a job in the computer science area, one place where there's really high demand is what they call interface. And this is mostly for video games, but it's also for flight simulators. The thing that's displayed in front of you that lets you act as if you were flying the plane. So you see the field or you see the sky and so on. It's that interface that lets you use your expert responses, doing what you normally do, turning the plane, banking it, all that. That's what makes possible the flight simulator and this separation between the expert and the programmer. So interfaces are critical. And any of you that have seen something like Second Life or Spore or something like that, you quickly realize how much the interface, what's displayed, makes that interesting and exciting. The same thing is true. Now, let me ask you, we've talked about corporations as a complex adaptive system. Do you know of any flight simulators for corporations? Anything where, you know, a CEO can go in there and make his decisions and see what it does to the corporation? I don't know of anything at that level. I know of some training tools along that way, but I don't know of anything where a serious executive like a pilot can really go in there and say, well, now, if I do have this 95% failure rate in my research, what effect is that going to have on the corporation? I don't know of anything like that. It certainly, it seems to me, would be much more valuable than a spreadsheet as a way of making predictions. Models based on building blocks. I'm going to say a little bit more about building blocks, but I think this is a critical way. Let me give you an example, and I won't say much about things like finitely generated groups, but consider some major invention of the 20th century, the internal combustion engine. Now, that really changed our whole lifestyle, incredibly so when you stop to think about it. What about that? What was new or innovative about the internal combustion engine? We knew about gears and wheels for literally millennia. We knew about pumps for a long time. The carburetor is Venturi's perfume sprayer, which was at least 100 years old at that time. Volta's sparking device. You can go down all the list of parts of that engine. We knew all the building blocks for a long, long time. What was new was combining them in a new way. So if we again talk about things like crossbreeding, crossbreeding is where I have various well-known building blocks like long legs in one horse and solid shoulders in another, and I crossbreed and I put the two together. That kind of thing is a way to produce innovation with well-known building blocks. In biology, this is known as recombination, and it is perhaps the most important thing that goes on in genetics. Another thing that we see, and this goes back to this notion of hierarchy, is how do boundaries and signals form and co-evolve? Go back to one of the earliest examples in economics. Adam Smith talked about the transition from an individual craftsman who made the ordinary straight pin to an early production line where one person drew the wire, another clipped it, another sharpened it, another put the head on it, you know, a simple production line. That lowered the cost of the straight pin from an article that only the wealthy could have to those, a very common item. It was a factor of 10 that initially lowered the cost. Now, that's really about boundaries, right? It's about how does this step pass something on to the next step, pass it on to the next step, pass it on to the next step. How did those boundaries form where there weren't any boundaries originally? There was just the original craftsman. Okay? And how do they signal each other? How do they pass things along? Well, we, even after all this time, in Adam Smith's example, we don't have any good computer model of this transition. So I claim that study of things like signals and boundaries, how they form, how they co-evolve, and so on, is central to understanding an awful lot, especially about hierarchy. And, well, that's a whole subject in itself. I won't. Complexity studies in computer science. One thing, some of you who know something about computer science have heard about the so-called NP-hard problems. These are problems that grow exponentially in difficulty as the size of the problem grows. A common example is the so-called map coloring or graph coloring problem. You have a graph with a bunch of nodes. You have a set of colors, let's say 3 colors, and you want to color every node in the graph, in the network, so that no 2 nodes that are connected have the same color. The early version of this was you could color any map of the world with 4 colors. And that took quite a while to prove. Okay, so there is this notion of these hard problems. The number of nodes, as it goes up, this problem just gets exponentially harder. What they didn't study was the fact that people just recently, within the last 5 years, started studying individual problems. And you find out the following thing. If I've got a graph with 10 nodes in one color, what do I know right away? I can't solve it, right? If I've only got one color and 10 nodes, there's no way that I can keep them in different colors. If I have 10 nodes and 100 colors, then the other way, I know it's easily solvable. Well, if you plot a graph from easily solvable to difficult to unsolvable, you find that it's a very narrow peak in the total set of such problems. And this is really surprising. So it says that most of them are pretty easy. There's just a very narrow peak, and the width of that peak decreases proportionately as the problem gets more and more difficult. So there are these sudden transitions from very easy, very narrow range of hard, and then very difficult. And these sudden transitions seem to be very common in complex adaptive systems. And again, if we study these transitions, I think we'll know more about this. One kind of transition is in language. It's been held for Noam Chomsky and his notion of universal grammar completely transformed the study of the language in the middle of the 20th century. And he gave a formal method, but it said nothing. In fact, they claimed that there was so little stimulus to a newborn child that the grammar that's used in language had to be wired in. Perhaps, however, what we're seeing is one of these sudden transitions where some fairly simple abilities that primates have just been turned enough together to make a sudden transition to the ability to acquire language. Now, we can actually back this partially. So this is not all conjecture, but it's an interesting alternative explanation to the wired-in grammar notion. Okay, I just repeat this for the moment that we're talking about interactions that are conditional and nonlinear, and reduction still works, but I have to study not only the parts and then add them up, because the whole really is more than the sum of the parts because of the interactions. I have to study both the parts and the way they interact. And so I still call that reductionism, but the classical notion of reductionism is you study the parts and you just add them together to get the whole. Okay, on to building blocks, and here's the business about the internal combustion engine, so I won't repeat that again. You notice that in the sciences, building blocks are the most common thing. We've seen this all our life. You start at very small particles, you put them together, you get particles at the next level, you put them together, you get particles at the next level, and so on. So if I look at something like the atom, it's made of protons, neutrons, and electrons from the next level, and when I put atoms together, I get molecules. And that's just at the level of the atom. The big advance was the periodic table, where I could see that how each of these things could interact. That's the interaction part. Okay. Interesting thing, I don't know, most of you have probably not been to Bergen, Norway, but it's very easy to predict the weather in Bergen, Norway, and every month except May, it will rain, and rain a lot. A man who made a tremendous difference in weather forecasting came from Bergen, Norway. He was a scientist there, and he was the one that came up with the notion of weather fronts. Weather fronts became the building block for predicting weather. It's what you see on the weather map every night, these fronts that are moving across. And it increased the weather prediction accuracy. Interestingly enough, you'll be 60% accurate, better than random, if you just say the weather tomorrow will be the same as the weather today. He went up from 60% to 75% by using this notion of fronts. So getting the right building blocks for the question you're trying to answer is, I claim, very important, and fronts were the right building blocks for weather. Now, here's another set of building blocks for faces. I'm going to pick 10 features like hairstyle, forehead shape, eyebrow, and so on for face. And I'm going to have 10 alternatives for each feature. And I'm going to call each of these alternatives a building block. Now, here's a question I ask my graduate students all the time, and only about 1 in 2 or 3 or 4 will answer. How many building blocks are there here? 10 features, 10 alternatives for each feature. How many building blocks? Here, 100. Anybody else go with that? Yeah, if I read, it shows you how phrasing could make a difference. If I say you have 10 sacks with 10 blocks in each sack, how many building blocks do you have? It's easy to get to 100. Well, these are the same thing. How many faces can you make? 10 times 10 times 10, 10 to the 10th. Huge number of faces from a very limited number of building blocks. Claim the reason we're very good at recognizing human faces is because we have the right building blocks. If I go to the zoo and try to recognize chimpanzee faces, I'm not going to be very good at it unless I'm a keeper there. I just don't have the right building blocks. So one major claim is, with building blocks, certain things become possible that are not possible otherwise. The second thing you get is, here is a complex geometric figure represented by a string of numbers, by just numbering each building block that's present. So I've got, in that particular figure, I've got eyebrow shape 1, I've got eye shape 4, I've got nose shape 2, and mouth shape 3. So I can represent a complex geometric object by a string, which is very handy when I'm trying to do stuff on a computer. Now, just one more thing about building blocks, and here I've got 7 of the ordinary children's building blocks. And you can see the combinatorics go up hugely. I've got 4,000 possibilities with 3 blocks. If I go up to about 20 blocks, it's, astronomical. Now, interesting thing, I could ask a child to build a castle with blocks. And if I do that, a 5-year-old or a 6-year-old, they'll do it pretty quickly. How can they do that with all those alternatives? Certainly not at random. Part of it is the child has a vision of what they want to get to. But they also have, notice, those 3 at the bottom, that's an archway. They learn to do that earlier. And that becomes a building block 1 level up. Notice that the one up at the top is a tower. So if I learn some of those, which are rather easier to learn, then you'll notice that the castle is made just exactly of those things. It's not, and suddenly, because I can do this hierarchy kind of thing as we did with atoms and so on, I can do things much more complicated than I could do it otherwise. Oh, this is nice. This is a lecture room with a clock. Usually they build lecture rooms so the lecturer can't see the clock. Okay, here's crossbreeding. I have 2 faces here, genuinely made from those parts. And crossover is literally what it says. You take 2 strings, you pick a point at random, and exchange the left-hand end of the 2 strings, as we did here. What happened? Well, I really got 2 new faces, didn't I? Just using the standard building blocks because I crossed over. Now, let me tell you a fanciful experiment that you can try on a psychology class. I'm going to give you 10 faces made from these building blocks, made at random. So they're just random faces. But we see that any combination of building blocks is going to yield some kind of face. So I give you 10 faces. Now, the interesting thing is I can ask one member of my class to classify those, rank those faces as to honesty. Now, none of us can write that down, but students will never complain. What do you mean, try to do that? They'll do it. Now, this isn't just students. Most people will say, oh, that's an honest face. That's a dishonest face. And we're not talking about current political elections. We do that as a very ordinary kind of event. Okay. What I'm going to do is the following. I'm going to give you these 10 faces and ask you to rank them, one of you. And then I'm going to take those things and do crossover of the faces that are ranked highest. So I'm just going to do this crossover for the faces that were ranked highest. It's very Darwinian, right? Natural selection, selection for honesty of face. Okay? I get 10 more faces, do crossover of the best. I can guarantee you that 5 generations of that, and you will think every face, whatever your criterion was, in the 5th generation was more honest than any face you saw in the 1st generation. And that's the way right combination works in biology, is just like that. And the nice thing is, if you actually do this experiment, now I can go back in there and see what building blocks do these faces hold in common. So I can even begin to analyze why you think the face is honest. So that's part of the reason for doing these exploratory models as well. And there you've really, I'm not going to spend much time, you've really seen what's really critical about genetic algorithms. In the case of genetic algorithms, however, we can prove theorems about this propagation of building blocks. And just to make this point solid, take one generation of humans and then go to the next generation of humans. There is no person in that next generation that is a copy of any person in the previous generation, right? What information is being preserved from one generation to the next if there's no copies? Well, by now, you can possibly guess my answer. Building blocks. What's being propagated is certain combinations of building blocks. The way to build a nose, the way to build an eye, certain combinations, and so on. So what is passed from generation by, we only get one Einstein. We don't get a copy in the next generation. So unlike most optimization processes where you try to work from the most recent one, instead you work from these recombinations. And what's being passed forward are certain combinations that work well. So if you've got a set of genes that, for instance, give you resistance to the new highly invasive staph germ, that's going to be passed on to the next generation because that's an increasingly selective feature. Unfortunately, I don't know any way to do that about automobile accidents. It doesn't seem to be working. I'm going to skip the details here. It's just about the theory. But genetic algorithms, part of the reason that for some people they're popular is that they're very easy to execute on a computer. You evaluate, that's the business of ranking the faces as to honesty. You then duplicate, and then you do the recombination. That's all there is. And these are all fast computer operations. So you can run genetic algorithms really pretty rapidly. And again, this is just showing the crossover operator. Okay. So here's a summary of what I've been trying to say, and then I'll go on to say a bit about it, cross-disciplinary research. I would say that the study of these complex adaptive systems, more than anything else, involves 2 steps. One step is carefully phrasing your question, getting the question in a way that makes it susceptible to some kind of simulation or theoretical attempt. And then spend time to discover the building blocks. What are the things that are at the center? Again, we can go back to the flight simulator. What are the building blocks for the flight simulator? Well, what you have, as in a car, is a control panel. That's the critical information. What generates that information? Those are the building blocks of the system. So there are ways to do this, to discover these building blocks. They're, as always in science, the early step is intuitive. It's not deductive. But you can gain some skill at doing this. And the claim is that innovation is primarily a matter of recombination of new building blocks, not a matter of describing or finding, recombination of old building blocks, not a matter of finding new building blocks. Most innovation, most of the innovations we know about are a matter of recombining building blocks that have been well known. And this is true in biology as well. And then simply for our attempts at this, where we're looking at these agent-based models, we use genetic algorithms by crossing over the rules of the agent to get new rules. And these rules act not as facts, but as hypotheses to be tested. And so recombination is a nice way to get new hypotheses. Okay. Hazards of interdisciplinary research. The Santa Fe Institute, which most people would say is the center, actually World Center for the Study of Complex Systems, has a very interesting method of working. First of all, the people that are there are invited there, and this started off with being really the work of one man, George Cowan, not widely known, but what they call out there a low badge number at Los Alamos, which means he was there during the Manhattan Project. George has a real talent for picking very talented people who are willing to listen as well as talk. And so those early groups were an exchange. They weren't somebody like Ken Arrow getting up and holding forth on the Arrow-Debreu theory. Ken instead engaged in all sorts of discussion. And he's very good at that, by the way. So one thing, if you're trying to do this kind of cross-disciplinary stuff, there may be people that are very prominent in the field, but they're only interested in giving you their ideas. They're not interested in hearing what other disciplines have to say. So it's critical that you form these working groups. And then at the Santa Fe Institute, what goes on is if the working groups bumps into some neat questions or things that look like they can study, then you begin to form workshops. People come out and spend a month or 2 months and so on, and you begin to push on these problems. So this is one way, but notice this is risk-taking again. Of those working groups, a lot of them will come to nothing. The people will get together, they'll have a great time, but they won't come up with any questions that are really can be pressed on. And so as far as the Institute's concerned, that's something they tried and didn't work. That goes on all the time out there. And the other thing that you have that's very Darwinian is because almost everybody at the Santa Fe Institute has their major appointment at some other university or some other institution. As they say out there, they vote with their feet. If the question isn't interesting to them, they don't show up. Now, there are very few places where that's true. If you work in a think tank, you're an employee. You can't just not show up. But at Santa Fe Institute, that's a very important part of the way they work. So, I would say again, if you're going to do cross-disciplinary stuff, these working groups are important. They mean having an easy place for the people to gather and talk, and it means that there should be some funds to make this possible, because they're not very expensive, but they're not free. You've got to pay transportation costs and so on. And I really don't have to say too much about this. This is what I've already said about how the home runs pay for the other. The hardest time to find funding, and this is true at the Santa Fe Institute too, is to go from this point where you're just paying the price for people to travel in to have them be there over a period of time. And sometimes this works out very well with respect to universities. If people have a sabbatical, they're happy to come. But other times you may have to pay salary as well. Okay. The overall thing is difficult, especially for people who are young faculty, because first of all, departments, with some reason, want you to publish in their major journals. They want to know that your paper can be refereed and acceptable if you're in physics, in the major journals in physics. If you're economics, the major journals in economics. Unfortunately, if you're doing work, the more original it is, the less likely it is to be accepted in these standard journals. They have well-established criteria. New work doesn't usually meet those criteria. And so the typical thing, and unfortunately, at least in my opinion, more and more in universities, because time is short and for all sorts of reasons, I'll just use a pejorative name, bean counting, looking at the citation index, can be the major thing in whether you get promoted or not. It's just sad but true. And the other thing is, often if you publish something new, you're almost inevitably going to step on the toes of somebody who's worked in the field. It's just, it's implicit that you're somehow saying their work is not as fundamental as they thought it was. So the thing that I would most recommend, which sounds very medieval, is to find someone that will be your patron. Find somebody that's well established in the area that will say, for your work, let them get on with it. Let her do this instead, and they'll stand up for you in departmental meetings and so on. It was critical for me and for most of the graduate students I know about, if you're doing cross-disciplinary research, this business of having a patron, and notice even Leonardo da Vinci needed a patron, is critical to getting on with it, to getting your promotion if you want to stay in academia, or to getting the necessary reputation to work in whatever place you want. So, the other ultimate revenge, and this only comes true when you're as old as I am, is to produce a lot of doctoral students. Eventually, they begin to overwhelm the opposition. So, I think that is it. I really like some questions if you have the time and want to ask them. Sure.
Recombination is a reuse of building blocks, but mutation is something different. And
True.
Possibly what you have is a combination. Most mutations are deleterious. So every now and then they actually generate a new building block. So you raised early on the absence of truly open systems. I wonder whether it's that combination and changes of the environment that might give rise to the open-ended innovation that you were talking about.
It's a nice point. The first thing I'll quote is just from biology. The probability, just the probability of a point mutation is 1 in a million. Recombination takes place in every one of us, in every generation. So in terms just of influence, recombination certainly has a huge influence. Now, nevertheless, occasionally a mutation will produce something. And in fact, the very first book I read in this, Fisher's Genetical Theory of Natural Selection, concentrated totally on the mutation aspect. And occasionally, and this is true in science, we come up with a new building block at some level. Now, again, there's this levels business. The transistor was a new building block. But in fact, one level down, we knew everything about semiconductors and all that kind of stuff well before the transistor. So there's this business. But mutations can have an effect. I think, let's see, this open-ended evolution is difficult because I can get perpetual novelty with just a random number generator. What I have to do is get this kind of coherent kind of thing that I get a complex adaptive system. We do use mutation in genetic algorithms. We just tune it down way beyond what you would normally think about. Yeah. But it is, I think, you don't want to do without it. Because if you lose all the genes at one locus, because for some reason they're not very good or something like that, then you've cut your search space in half. Yeah?
In your face model where you recombine the different building blocks to get new phenotypes, it's worth noting that in biology, even though the building blocks structurally remain constant, except in mutation, their functions don't necessarily. There's a
Yes.
great deal of context dependence. And so it isn't always as straightforward as your particular
No.
example illustrates.
That's really right. The face thing is simple to understand, but not as far from what's actually going on in genetics. There's some, and again, you can even just modifying the transcription of the same gene, and now more and more we know that that happens all the time, can change the signals, which changes the feedback loops, you know, and so there are some things that are really standard building block. The Krebs cycle is in every organism from carrots to elephants, and it's pretty much standardized. It's, by the way, not the optimal. You could go in there and design a better cycle than the Krebs cycle, but it's standardized. And that means I can connect it into all these other systems. But the point you're making, and that's the reason I'm spending an awful lot of my time trying to see this coevolution of boundaries and signals, because that can change things just tremendously. You know, even from the simple idea, if I have a semi-permeable membrane and up the concentration of some particular protein, I've upped the reaction rate that involves that protein. Just, you know, something classical. Yeah?
Would you explain your model for the evolution of language?
I can say a few words. Actually, that's what I talked about this morning. But quickly, our model is the following. It's agent-based. We assume that we have some competent agents that know some language. We assume that we have some agents that know nothing about language, absolutely nothing, grammar or anything. We put them in an environment so that they have to find, say, food patches and water and things like that. And language only survives if, in fact, it helps these agents work together to get more of this resource than they could get in the control group, where we just don't let them have language. Okay. Now, what we do is we start with 3 pre-primate characteristics wired in. Ability to imitate, imprinting, that goes way down. The ability to distinguish object and action, and that's this reflex that causes you to look off to one side if there's something fast moving in the periphery. And the other thing goes back to animals that hunt in packs, and that is for the 2 of them to be mutually aware that they're looking at the same object. We think that from those wired-in characteristics and the exchanges that go on in a child and a mother, say, that we can get up to the stage of proto-grammars where the child is uttering, say, get milk in the right order, and part of what we expect to find here is that child early on will just say milk. And that may mean get milk, it may mean there's a milk bottle over there, it may mean that my sister is grabbing the milk bottle. To reduce the ambiguity, you add a second utterance, and that helps the child clarify the situation. Our claim is this is pretty important. Now, one thing, and this is one of those gee whiz facts, but it really, as my daughters would say, blew me away. I have a colleague in Singapore at Nanyang Technical University who taught in mainland China, got her degree at Lund in Sweden, and taught at University of Toronto. So she's fluent in English, Chinese, and Swedish. And by the way, if you want to see something, I kid her about this all the time. It's rather funny to see somebody that's Chinese speaking English with a Swedish accent. Anyhow, her work in data was the following. She looked in all 3 language groups at young children that were acquiring their first action words, like beat or hit or something like that. Across the board, she found that these children did not acquire these words in a repeatable way until they could do the action. And that's just, that was really, you know, now we all know that people talk with gestures. Everybody. Italians more than most. And the question is, what's the relation between gestures and utterances? How does language develop as a combination of these kinds of things? Well, this begins to tie some of that together. It's very interesting to me. And so we're trying to build our models around some of this data. Danny.
John, you noted that it's almost prevalent in complex systems that they're built in a hierarchical structure. I wonder if you just have your own personal conjecture of why you think this is the case.
Yeah. Here I can, how to say it, give a plug for a forthcoming book, which probably won't be done for 5 years, although I am on chapter 8 of 11 or 12. I think that this comes about because of the coevolution of what I'll call boundaries, which might be membranes and signals. And if I have a semi-permeable membrane, only certain kinds of proteins can go through that membrane. If I change the signal, that may change whether it can go through. If I change the membrane, it can change what it goes through. And so what I'm trying to do is use this complex adaptive system approach to watch the coevolution of boundaries and signals from very simple systems to, I would claim, systems that get more and more specialized. So this is a little bit like the transition from the craftsman to the production line in Adam Smith. I expect to see this kind of thing going from, general purpose things that become more and more special purpose. Like in the tropical rainforest, they build their own niches, there are more interactions, all kinds of symbiosis and predator-prey relations going on. That's what I hope to be able to say something about. I think it's, for me right now, obviously if I'm working on it, it's the most critical question, right? Yeah, Mike?
Well, these are comments, but also relate with some of the questions. Facilitated theory of evolution by Kirchner at Harvard. What he argued is that random variations and what is new phenotype depends on the phenotype which exists at the time.
Yeah.
It is facilitated. It is not that the random variation gives novelty.
Yeah.
Rather, it is facilitated by the phenotype which exists.
Yeah.
And that is what makes biology uncertain.
Yeah.
Because everything has to be explained in terms of evolution. Right?
Yeah.
Meaning going back and back and back and back.
Yeah.
And the second thing, or building blocks, right? Genome of the mice and the human is about the same.
Yeah.
What is different is regulation.
Yeah.
How they are organized.
Yes.
So in addition to building blocks, we do not inherit just genes, but also how these genes are organized, and this is why human and mice are different, right?
Yeah.
Because not that the genes are different, but rather the number of genes are different, but rather they're organized. So what I'm saying is, in addition to building blocks, right, this procedure, how to organize, right, is what gives us the complexity that we're talking about.
An example that I could give along a similar line, for any of you that have ever done computer programming, you know that you have, especially if you get down close to the machine level, you have a limited set of instructions. In some cases, 32. But it's how those instructions are lined up and interact, and where your conditional feedback loops are and so on, your iterations and so on, your subroutines. Those are the things that enable two programs that may only differ in a couple of instructions do entirely different calculations. And what we know now is that we used to think of chromosomes as beads on a string, but chromosomes are more like instructions in a program. The genes get turned on and off, what proteins are already there in the phenotype. So this is back to the boundaries and signals kind of thing as far as I'm concerned. And what makes possible some of the complexity is there are things like subroutines. So the Krebs cycle is a kind of subroutine that I can depend on and use for certain kinds of purposes. And so those are the building blocks one level up. But how they interact, how I control the interactions is very much a matter of boundaries, semi-permeable membranes, and what signals can go through them. And as you say, those things are determined by the phenotypes that are already there. So, that's the reason we still study evolution.
Interaction, but rather how these interactions are organized.
Yeah. And if I'm going to try to change programs, computer programs, by recombination, I better be pretty careful where I make the cuts. Yeah.
Genetic algorithms have been applied in optimization for the last 20 years, and they are competing, so to speak, with simulated annealing algorithms.
Oh, yes.
Do these kind of algorithms apply to your problems, and how do you see results? In optimization, we find that sometimes genetics win, sometimes simulated annealing produces better solutions.
Yeah. You just have to take my biased comments into account. But first of all, and Danny modified this when he was introducing me, I think of genetic algorithms as more a way of finding improvements, not of optimization. Simulated annealing, however, is essentially an optimization algorithm. So if I look at a very difficult problem like designing a new kind of high bypass jet engine, simulated annealing is only going to work when I'm pretty close to what I say is the best I can do. Whereas we would use genetic algorithms early on to try to find, well, if I put these things together this way instead of this way. Now, this was actually done at General Electric. And so they didn't try to use simulated annealing, but they tried to use their expert system for simulating engines, and then they started recombining it. And they got a really weird design that was 3% more efficient than the best engine they could design, which is tremendous in an area like that, which has been so heavily studied. So I would simply say that if you have a problem where there are lots of possibilities and where you're trying to get an improvement rather than an optimum, that I would tend to lean towards the genetic algorithm. If I've got a problem where I have a pretty good idea of the location of the peaks, or at least the valleys, depending which way you look at it, then simulated annealing can do pretty nicely. So these, and as always, there are areas in between where it's, but you know, for instance, I would never use a genetic algorithm to try to climb a single hill. Conjugate gradient methods are, you know, double the accuracy on every iteration. I mean, on the other hand, if I've got a completely random problem, no algorithm's going to do me any good. I might as well do random search. In between are these various classes of problems where you've got things like genetic algorithms, genetic programming now, simulated annealing, and various kinds of branch and bound techniques that in neural nets back propagation, and so on. And there you have to, you know, as always, you have to use some judgment as to what you think is going to happen.
Thank you.